existence of derivatives. So a function is said to be differentiable. So what that means is that there is a derivative at that point. Okay. So at the point A, if f prime at A exists, so of course, like this prime is the derivative. Okay, at points where f is not differentiable, we say that the derivative does not exist. Okay, so this wording specifically. Here are three common ways for a derivative to like not exist. So if there's a cusp, so if it goes down and then back up, the derivative right at that point A does not exist. Also, if there's a vertical tangent, okay, so if there's like kind of like a zigzag where right here, right at point A, there's a vertical tangent. Remember, the slope of a vertical line is undefined, therefore that does not exist, the derivative. Okay, or if there's like a jump, a discontinuity, and we're going to get more into discontinuities. We're going to see more examples, but if there's a discontinuity, so we know of a jump or if there's a hole. Okay, but no, it's possible for a function to be continuous at a point and yet not differentiable, because this cusp, we don't actually have to take our pencil off the paper in order to draw it, or this one right here with the vertical tangent, we don't have to take our pencil off the paper in order to draw it, but still at these points, they're not differentiable. Okay, so what we're going to do is we're going to show that the absolute value function f at x equals x, absolute value of x is not differentiable at x equals 0. Okay, let's get some more room. Okay, to start out with, we're going to do f prime at x equals absolute value of x plus h minus f at x. Oh, but f at x is just absolute value of x all over h. Okay, and this is limit as h approaches 0. Well, we can just straight sub in that 0. So we have absolute value of x, because this is 0, minus we can actually do this a different way. So let's just recall first, the absolute value function looks like this. Okay, so we know that there's a potential, like potentially at x equals 0, it's not going to continue. So let's actually sum in 0. So f prime at 0 equals the limit as h approaches 0. Okay, so this time we plug in 0 for the x plus h, absolute value, minus 0 all over h. Okay? And now when we simplify, we just get the absolute value of h over h. With this absolute value of h, what we have to do is we have to consider both cases. We have to consider case number 1, the limit as h approaches 0 from the left-hand side. Okay, so as it approaches 0 from this left-hand side. And then we also have to consider the limit as h approaches 0 from the right-hand side. Okay, and again, this is from the right-hand side. Then it gets really easy. So from the left-hand side, our equation is negative h over h. If we cancel these, our limit is negative 1. From the right-hand side, our equation is h over h, so our limit is 1. Therefore, the limit does not exist. Limit does not exist. So we talked about how the limit does not exist if there's a cusp or a crease or a vertical asymptote, okay, or a vertical tangent, I should say, if it's discontinuous or if it's discontinuous. So in this case, the limit does not exist because the limit of the left-hand side does not equal the limit of the right-hand side. Okay, we're also going to get into more notation. We talked about f prime at x. We're also, when we are given y, we have to match it up to dy by dx. We're going to see that. If we're given f at x, we're going to have to match it up to f prime at x. Okay, it depends on what you're given that dictates the notation that we use. And this dy over dx is actually just read dy by dx.